All right. So this is 3.4, part B. This is on the kinematic, not kinematic equations. That is, position, velocity. I'll say velocity / speed, and we'll talk about the difference. Acceleration, and something the book doesn't cover, but it's part of it, the jerk. So, position. We've seen this. We've used this. Position is S of t. That's our position function. If we take, it's called the time derivative, or ddt of S of t. This is the rate of change of position with, I'm going to move this down to the next line. Respect to time. In fact, this is a common phrase. The derivative with we often say with respect to. And it gets said so much, we abbreviate it to WRT. And what it does is it's whatever comes after represents what variable the derivative is affecting. Now, in Calc 1 and even Calc 2, this doesn't really change. S of t has only one variable. But in Calc 3, we will have functions like f of x, y, z, and then being able to say the derivative with respect to y tells us which variable we're treating as a variable, and we're going to treat the others as constants. That's for another day. I just want to show you what WRT means. So the time derivative of the position function, S of t equals position. Time derivative gives us S prime of t. And this is the velocity function. And we usually call it v of t. Where speed is connected to this, maybe I'll change the order of these real quick. So where speed comes into this, speed is the absolute value of velocity. There's a little more to it. When we do Calc 3, velocity has a direction. Speed doesn't. And here, like velocity has a direction as well. Positive is like how fast are you going forward? But if you're driving in reverse, you would have a negative velocity. And so speed is still how fast you're going in reverse. It's that kind of idea. If we take the time derivative of velocity, we get v prime of t, and a change in velocity with respect to time. When your velocity changes over time, you are either accelerating or decelerating. So we call this acceleration. Where deceleration is when a of t is negative. Your acceleration is negative, which means you're slowing down. I don't know if that doesn't look right. There's only one c. Why does acceleration have two c's, but deceleration only has one c? That looks funny, but I'm pretty sure that's right. And so a of t is v prime of t, which is the second derivative of the position function. And finally, when we have a change in acceleration, over time, think of braking really hard. You're in the car, you're going really fast, you see the cops, you're like, fuck, I don't want to get in trouble. You slam the brakes, which is bad. They see the nose of your car dip down. They already know you're speeding already. But if you slam the brakes, you get a little bit of whiplash, your head jerks forward. This is called the jerk. And oftentimes jerk goes by J of t. J of t is the derivative of acceleration, which is the second derivative of velocity, which is the third derivative of position. I don't think there's anything in the textbook with jerk on it at this point. This is just a Hefe bonus. So let's take a look at some examples here. Let's say the height of a ball above ground in feet t seconds after it is released follows the function s of t equals negative 16t squared plus 144. Question A, what is the instantaneous velocity when it hits the ground? And B, what is the average velocity? Okay, so just to give you an idea of what's going on, if we say t equals 0, this is when the initial release of the ball. S of t equals 0 is negative 16 times 0 squared plus 144, which equals 144. So this is like a y-intercept kind of, and it represents starting height. And this is why this thing is often called S0, because it represents, it's kind of shorthand notation for S of t equals 0. So it's starting 144 feet up. And the ball gets dropped and accelerating the ground. We need to find, we need to find how long it takes till it hits the ground. Okay. So when does it hit the ground? Well, it hits the ground when S of t equals 0, right? Which is the height equals 0. So we take our S of t and we set it equal to 0 and solve for t. This is a lot easier if you factor out negative 16 and you get t squared minus 9 on the inside. And I can divide by negative 16. That's not changing anything. I get t squared minus 9 equals 0. T squared minus 9 factors into t minus 3, t plus 3. And so since that equals 0, it means t minus 3 equals 0. That look like a 0. Or t plus 3 equals 0. And when we solve for these, we get t equals plus or minus 3. So what does that mean? What? Positive 3 is kind of like how long until it lands. And in this case, it's the only thing that's applicable. If I drew a little graph here, this is making a downward parabola like this, where this is representing the height, S of t, and this axis is time. So it's hitting at t equals 3. Over here is t equals negative 3. And it's kind of like what would have happened if the ball was thrown or kicked from the ground 3 seconds prior to the start. That's not really applicable here. We said the ball was dropped, so we don't need negative. So we have, that's when it hits the ground. T is 3 is when it hits the ground. So we want to find the instantaneous velocity. Instantaneous velocity, this is part A, is when s of prime, we want s prime of t. That's the instantaneous velocity function. We want it at t equals 3. But you have to do it with t by itself first, because if you plug in 3 right away, it becomes a constant and it doesn't help at all. So I have, that doesn't look like a t at all. Wow. We have negative 16, and the derivative of t squared is 2t, and the derivative of a constant is 0. So this just ends up being negative 32t. So when we evaluate it at 3, we get negative 32 times 3, which is negative 96. And this is going to be feet per second. Well, what is the average velocity? That was part A. Average velocity is, we do it at 2 points in time. We're doing s of 3 minus s of 0 over 3 minus 0. S of 3 is 0. S of 0 is 144. That's it, how high up it started. And we got 3 minus 0. This is negative 144 over 3. And if you divide by that, it's negative 48 feet per second. And so this represents how the ball is speeding up. It starts off a little slow, but then it starts going faster and faster and faster as gravity pulls it downward. So the average speed is just averaging out all that change in acceleration. Okay. That was a long section. I'm going to pause the video and we're going to do another video right after this on more velocity and stuff.